Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Vapor Liquid Liquid Equilibrium Part 2. In the previous lecture what we have seen different TXY phase diagrams of a VLLE system, that is where we have one vapor and then two liquid phases are coexisting. So, how their TXY diagrams would look like at a given pressure, and then if you change the pressure how they are going to change, those things we have already seen in detail in the previous lecture, right. We have also seen how to obtain equilibrium composition of this VLLE system, right, with equations, and then how we can segregate these equations in order to solve these VLLE problems, especially when the pressure is low to moderate. That is what we have seen. So, now in this particular lecture we will be taking a few example problems, and then we try to draw phase diagrams for this system from these example problems, right. Before going into the details of solving these problems, we will be recapitulating the equation part of equilibrium composition measurement for this VLLE problems, that we will be having a kind of recapitulation now. Okay. Equilibrium composition of VLLE. So, to calculate the equilibrium composition in VLLE, what we have to do? We have to set the fugacity of each species equal. So, that if you do, FAV is equals to FA alpha is equals to FA beta, and then FBV is equals to FB alpha is equals to FB beta. We are taking only binary system having A and B components. Now, this we know that FAV is equals to FA alpha is equals to FA beta. So, then if you write generalized one, YA Phi A P is equals to XA alpha gamma A alpha FA naught is equals to XA beta gamma A beta FA naught, these things. So, now depending on the phase whether it is ideal or non-ideal, so this Phi A and then gamma A terms would be there, right. So, if it is ideal phase, so then these can be taken off. If it is non-ideal, accordingly corresponding equation depending on the which model have been used for describing the non-ideality of vapor phase, accordingly Phi A expression will come into the picture, and accordingly which model for excess Gibbs energy is used to describe the non-ideality of the liquid phase. So, accordingly this gamma A beta gamma A alpha expression would come into the picture, right. So, if you have non-ideality in all three phases, solving these equations will become very difficult, because all these equations are non-linear, highly non-linear, and then obtaining composition by hand calculation become very difficult. So, one can write a kind of algorithm and then solve them, or also there are a few programs available, so that we can use and then obtain this composition, equilibrium composition for this such kind of non-ideal non-linear systems. Okay. However, for simplicity we take now vapor phase as a kind of ideal phase, and then liquid phase non-ideality described by 2 suffix Morgul's equation. That simplicity we take, and then we assume the pressure is low to moderate, and then do a few example problems. So, when you assume 2 suffix Morgul's equation for liquid phase and then vapor phase as a kind of ideal phase, then we have for component A this expression YAP is equals to XA alpha exponential of A by RT XB alpha square PA sat is equals to XA beta exponential of A by RT XB beta whole square PA sat. So, this is nothing but, this part is nothing but FA beta, this middle part is nothing but FA alpha, and this is nothing but FA V. This is we have written for component A. So, there are two independent equation, first term is equals to the middle term, one independent equation, then first term equal to the third term is other independent relation, or you can take the second and third terms are equal as a kind of independent equation. If two are independent, third one cannot be taken as independent. So, two equations are there, right. Similarly, for component B, if you write, you have two equations like this. So, 4 equations, and then in addition to that one, the mole fraction of summation of mole fraction of all the components should be equal in each phase. So, these three relation, because three phases are there for vapor phase, for alpha liquid phase, and then for beta liquid phase. This should be XA XB alpha, XB alpha, XA alpha plus XB alpha is equals to 1, right. So, now we have how many unknowns? YA, YB, XA alpha, XB alpha, XA beta, XB beta, P and T are the unknowns, right. So, depending on the phases are existing, and depending on the component, you can use the Gibbs phase rule to find out the minimum degrees of freedom. So, accordingly those depending on the degrees of freedom, you can fix those many independent variables, and then remaining independent variables you can calculate using these equations. So, now here these 8 variables are related by these 7 equations. Okay. All these 7 equations have to be solved simultaneously to obtain reliable VLLE composition. Further, 4 of these equations are non-linear in nature. Their solution by analytical methods may become very cumbersome. For liquid system, their activity coefficients are almost unaffected by the pressure, provided it is in the range of low to moderate pressure, that we already know. So, making use of that benefit, that liquid phase non-ideality, or the activity coefficients of liquid phase are independent of the pressure. So, then whatever the equation number 1 and 2 that we have given, that is the equilibrium relations for VLLE problem for both the components, that you can segregate in 2 parts. You can segregate in 2 parts, and then one part you can solve the equations only taking the LLE terms, and then solving the LLE composition exactly the similar way as we have done pure LLE problem, where there is no vapor phase at all, only 2 liquid phases are coexisting. Once you have this LLE composition, that you can use, and then you find out vapor composition, so that all these 3 phases composition you can find out, vapor, 2 liquid compositions you will be finally obtaining. But this segregating approach you can use only if the pressure is low to moderate, you cannot use it if the pressure is high. So, this is what we have seen in previous lecture, it is a kind of recapitulation. So, now what we have, we will take an example problem. A binary mixture exhibit vapor liquid equilibrium at 300 K. The excess Gibbs energy is given by 2 suffix Morgul's equation with A is equals to 6235 joule per mole. Determine the composition of 3 phases and total pressure. The saturation pressures are given as PA_SAT 100 kilopascals and PB_SAT are 50 kilopascals, that is 1 bar, and then less than, it is approximately 1 bar PA_SAT, and then PB_SAT is approximately 0.5 bar. So, their saturation pressures are very low. So, then what we can say, the activity coefficients of the system of this whatever the 2 liquids are taken binary mixture. So, they can be treated as independent of pressure, because these saturation pressures are low for these 2 components. We can treat the activity coefficients of this liquid system as independent of pressure. So, then that we can have a kind of segregation of LLE part from vapor part in the equilibrium relations of VLLE, and then solve the equations as we have described in a previous slide. So, we have for component A and then component B, we have these relations. Okay. Now, for liquid alpha phase, XA alpha plus XB alpha should be 1, and then liquid beta phase, XA beta plus XB beta should be 1, and then for the vapor phase, YA plus YB should be 1. These are the relations. Okay. So, how to solve them? Okay. We have to solve these equations, non-linear equations, in accordance with these things, and these equations should be satisfied, then only we can say the reliable solution. Saturation pressures of 2 components are in the low to moderate range. Therefore, the liquid equilibrium composition can be safely assumed that it is unaffected by the pressure. Accordingly, one can solve LLE composition independent of vapor composition, wherein the pressure term occurs in the equilibrium relation in this equation number 1 and 2, whatever I have written in the previous slide. Okay. Then calculate the composition of vapor that is in equilibrium with the 2 liquid phases simultaneously, for whose composition we have already obtained by this LLE calculations. So, this VLLE problem, what we are doing, we are segregating as first LLE problem, finding out their composition, and then using this composition, that is XA alpha and then XA beta, that we are using, and then finding out the vapor composition, that is YA. That way we are doing, okay, because the pressure is in the low to moderate range. So, first obtain the LLE composition by solving equations of LLE part only following the trial and error solution procedure described in LLE lectures. What we have done there? We have to assume a value of XA alpha, and then using equation 1 in the previous slide I have written, compute XA beta, and then from equation 3 you obtain what is XB alpha. Then using equation 2 you compute XB beta, right. So, now all the values are obtained, XA alpha, XB alpha, XA beta, XB beta you have got, though with a starting assumed values. Then you have to check if equation 4 is satisfied or not, that is XA beta plus XB beta is equals to 1 or not, this is what you have to check. Why we have to check? Because this XA beta and then XB beta we are calculating this using equation 1 and 2, which are the primary equations of LLE. So, if this obtain XA beta and then XB beta, when you add them together, if it is coming close to 1, then assumed value of XA alpha is reliable, and then that can be taken as a solution. Otherwise, what you have to do? You have to assume another value of XA alpha and then repeat the calculation until this equation satisfied. Okay. Continue these steps until equations 1 to 4 are simultaneously satisfied. Okay. So, then when you do this thing, then you will find XA alpha is equals to 0.855 for this problem, and then XA beta you will be getting 0.145 for this problem. Okay. So, now solve VLE part as described below. So, what you can do? You can take this equation, two equations are there, whatever the P is equals to YA P plus YBP is equals to this one plus this part. Okay. Whatever the equation number 1 and 2 are there, if you add them together, then we have this equation, because that we have written for component A and component B as well. So, we are taking for the component A part. That you can do, you can take I mean like we can take this vapor and then alpha liquid phase part that we have taken. You can take vapor and then beta liquid phase also, and then similarly you can find out the pressure. Okay. So, then you will get P is equals to 135 kilopascals, and then YA is equals to nothing but XA alpha exponential of A by RT XB alpha whole square PSAT by P is equals to 0.667. So, that is you are equating this equation, probably I will write again. So, YAP is equals to XA alpha exponential of A by RT XB alpha whole square PSAT is there, and then this is also equals to XA beta exponential of A by RT XB beta whole square and then PSAT. This is one equation for component 1, right, and similarly if you write for the component 2, that is YBP is equals to XB alpha exponential of A by RT XA alpha whole square multiplied by PB sat is equals to XB beta exponential of A by RT xa beta whole square multiplied by PB sat. So, what I have done, I have taken only this part of two equations and then added them together. Then I have this equation YAP plus YBP. So, that is nothing but P into YA plus YB, that is P, and then equals to this particular part of from the component A this particular part, and then from component B this particular part. Okay. You can do other way also. YAP you can take equal to this part, and then YBP you can take equal to this part, and then obtain the pressure, you can get the same thing. Okay. And then for the YA, again once I found the P, I have used only this part of the equation to find out this YA, that is XA alpha exponential of A by RT XB alpha whole square PA sat by P, when I substitute all these values, because PA sat, PB sat values are given in the problem. XA alpha, XA beta we have already found. So, XB alpha, XB beta are found anyway. A is also given, temperature is also given, everything is known, and then pressure we just now found it as 135 kilopascals. So, then it comes out to be 0.667. So, pressures kilopascal small k should be there. Okay. So, this is how we can see. Now, XA alpha we found. So, XA beta we found, and then YA also found, that is all three phases alpha liquid, beta liquid and the vapor phase are coexisting, and they are at equilibrium and then coexisting and equilibrium. So, their composition we have found using this way by segregating them. Okay. So, this is how we can solve these problems easily. Now, what we do? We take another example problem. Use the Van Laer equation to estimate the composition of the coexisting liquid phases in an isobutane and furfural mixture at 37.8 degrees centigrade and a pressure of 5 bar. Van Laer constants for the system are given as A1 is nothing but 2.62, B1 is nothing but 3.02. So, that is first part, that is only LLE part is there. There is no vapor. Okay. In the second part, by assuming the liquid-liquid equilibrium of above system is unaffected by pressure, it is given, already given. So, we do not need to make an assumption, or we do not need to check at the vapor pressure, saturation pressures or the total pressure of the system. It is already given that assuming the LLE of above system is unaffected by the pressure, compute the pressure at which the first bubble of vapor will form. That is, computing the bubble point pressure of the system is required, and also composition of the vapor that forms. The P1 sat at this temperature and then P2 sat at the same 37.8 degree centigrade are given. P1 sat is 4.956 bar and then P2 sat is 0.005 bar. The saturation pressures are anyway very small. So, then obviously, the activity coefficients of liquid phases or the LLE behavior would be unaffected by the pressure. Okay. So, now here this is VLLE part coming into the picture, but VLLE part is such a way that LLE part can be segregated from the vapor part in solving this problem, because LLE part is unaffected by the pressure, that is already given. And also you have to draw the phase diagram of this system, that is we have to draw PXY diagram for this system. Okay. So, for LLE component 1 and 2, if you take x1 alpha gamma 1 alpha is equals to x1 beta gamma 1 beta for component 1. So, x1 alpha and then gamma 1 alpha for Van Laer's equation is nothing but exponential of A prime divided by 1 plus A prime x1 alpha by B prime x2 alpha whole square is equals to x1 beta, and then gamma 1 beta is nothing but exponential of A prime divided by 1 plus A prime x1 beta divided by B prime x2 beta whole square. So, these equations for gamma for Van Laer equations that we have already derived in previous lectures, This A prime, B prime are given. Only thing that we have to find out what is this x1 alpha and then x1 beta, these things you have to find out. This is for component 1. Similarly, if you write for component 2, before writing component 2 what we do? We write this entire equation in terms of x1. So, wherever x2 is there we will be writing 1 minus x1. So, that this entire equation is in terms of x1 alpha and x1 beta, because rest everything is given, A prime, B prime etc. are given, or A1, B1 are given in. Fine. So, now for component 2, similarly LLE relation if you write is nothing but x2 alpha gamma 2 alpha is equals to x2 beta gamma 2 beta. That is x2 alpha exponential of B prime divided by 1 plus B prime x2 alpha divided by A prime 1 minus x2 alpha. It should be actually x1 alpha, but I am writing x1 alpha is nothing but 1 minus x2 alpha. So, that this entire equation is in terms of x2 alpha, and this part is square of this part is there is equals to x2 beta, and then gamma 2 beta is nothing but exponential of B prime by 1 plus B prime x2 beta divided by A prime x1 beta whole square, but x1 beta I am writing 1 minus x2 beta. So, that this entire equation is in terms of x2 alpha and then x2 beta. So, now we have two equations, and then two unknowns, x1 alpha and then x1 beta, because if x1 alpha is known, x2 alpha is anyway known, x1 beta is known, x2 beta will be anyway known for a binary system, right. So, these equations may not be sufficient, because if you solve only these equation by taking that x1 alpha is equals to x1 beta, any value of x1 in alpha phase and beta phase if you take and then equate them, then this equation would be satisfied, as we have already seen. So, but that is not a correct solution, because that should also satisfy these equations, x1 alpha plus x2 alpha is equals to 1 and x1 beta plus x2 beta is equals to 1. So, obviously these equations are exponential and terms are there, nonlinear equations are there, very difficult to solve. So, one can use the numerical tools that are available to solve these equations, or one can go for a trial and error solution method, as we have seen previously. So, all these equations 1, 2, 3 and 4 have to be simultaneously solved in order to get the solution, and then all these equations solving analytically is very difficult. So, one can apply numerical methods to get these solutions, or otherwise one can follow the trial and error approach that we have already discussed. So, the same thing we are going to follow here again. So, follow trial and error approach described in LLE lectures, that is, first assume a value of x1 alpha, then solve equation number 1 to get x1 beta, and then from equation 3 is nothing but x1 alpha plus x2 alpha is equals to 1. So, x1 alpha we have already assumed. So, x2 alpha you can find it out, what is 1 minus x1 alpha. So, that is x2 alpha. Once you know x2 alpha, using that x2 alpha you can solve this equation number 2 to get x2 beta. So, x1 alpha we assumed and then x1 beta, x2 beta we calculated, right. So, now this x1 beta actually x1 beta and then this x2 beta, when you add them together they should come equals to 1. But now what we are doing, we are getting this x1 beta and then x2 beta we are calculating from two different equations. So, that is the reason we have to check now x1 beta plus x2 beta is equals to 1, is it coming equals to 1 or not. If it is coming equals to 1, then solution is reliable, okay, or assumed x1 alpha is reliable and then obtained x1 beta is correct value. If that is not coming to 1, then we have to repeat these steps. Check if equation 4 is satisfied or not. Equation 4 is nothing but this one, x1 beta plus x2 beta is equals to 1. So, if this equation 4 is not satisfied by independently finding out x1 beta and then x2 beta from two different equation, and then by adding them together, if they are not coming equals to 1, that means the assumed value of x1 alpha is not correct, and then we have to update this x1 alpha or assume another value of x1 alpha and then continue the procedure till we satisfy this equation. Okay. Continue these steps until equations 1 to 4 are simultaneously satisfied and then get the answer. So, when you follow this procedure, then you can find out x1 alpha is nothing but 0.1128 and then x1 beta is nothing but 0.9284. Similarly, x2 alpha is nothing but 0.8872 and then x2 beta is nothing but 0.0716. What we can understand from these solutions, this alpha phase is rich in component 2, whereas this beta phase rich in component 1. The component 1 is almost 92 or 93% in beta phase, whereas component 1 is very small in alpha phase. In the alpha phase, component 2 is very rich, almost 88-89% of mole fraction of moles, almost 89% of moles of that alpha phase are of component 2. So, that is alpha phase is rich in component 2 and then beta phase is rich in component 1. Okay. So, now we have to find out activity coefficients also, because we have to use them for calculating this YA composition as well. So, gamma 1 alpha you can get 8.375 and gamma 1 beta 1.018 and then gamma 2 alpha 1.030 and then gamma 2 beta 12.77. These are using the Van Laar equations. Van Laar equations, whatever ln gamma expression that we have in terms of A prime B prime. So, they can be used for both phases, alpha and beta phases, and then solve simply substitution of this x1 alpha, x2 alpha or x1 beta, x2 beta etc. in those equations you can substitute and then get this equation. At the beginning of the solution of this problem, we have this equation written. So, there you can simply substitute for this gamma 1 alpha and then whatever the x2 alpha information is required, that you substitute, because A prime B prime are anyway given. Similarly, for the case of gamma 1 beta, whatever the x2 beta information is required, that you got already. So, you substitute, because here also A prime B prime are known, same A prime B prime are there. Similarly, gamma 2 alpha, gamma 2 beta also you can find out. Okay. So, now for VLLE what we can have? We can have Y1P is equals to x1 alpha gamma 1 alpha P1 sat is equals to x1 beta gamma 1 beta P1 sat. So, this is for the component 1. Similarly, for component 2, if you have Y2P is equals to x2 alpha gamma 2 alpha P2 sat is equals to x2 beta gamma 2 beta P2 sat. So, this is nothing but F1V, this is nothing but F1 alpha, this particular part, and this particular part is nothing but F1 beta. Similarly, this particular part is nothing but F2 beta, this particular part is nothing but F2 alpha, and this particular part is nothing but F2V, which are at equilibrium and coexisting and at equilibrium. Now, if you wanted to find out this Y1 or Y2, you need to know P, that is not given. So, first what you have to do? You have to find out what is the pressure. So, for that what you can do? You can add these two parts, Y1P is equals to x1 alpha gamma 1 alpha P1 sat plus the other equation Y2P is equals to x2 alpha gamma 2 alpha P2 sat. So, then we get, so when you add these two, then we have Y1P plus Y2P, that is nothing but P is equals to x1 alpha gamma 1 alpha P1 sat plus x2 alpha gamma 2 alpha P2 sat. So, x1 alpha you find out this one, gamma 1 alpha you obtain this one, P1 sat is given this one, and then x2 alpha you obtained as this one, and then gamma 2 alpha you obtained it as this one, and then P2 sat is given as this one. When you substitute all these things, you will get 4.69 bar. You can add these two also. These two parts also you can add, that is YIP part. If you equate with this beta phase equations, then also you can get, that is P is equals to or Y1P plus Y2P is nothing but P, and then that equals to x1 beta gamma 1 beta P1 sat plus x2 beta gamma 1 beta P2 sat. This one also you can do. X1 beta you got it as 0.9234, P1 beta it is this is what you got, P1 sat it is given 4.956, and then x2 beta you obtained this one, and then gamma 1 beta you obtained it as, and then gamma 2 beta, this is gamma 2 beta you obtained it as gamma 2 beta you obtained as 12.77, and then P2 sat is given as 0.005, then also you are getting 4.69 bar. Either way you can get it. So, once the pressure is known, then you can use either this part of the equation or this part of the equation, any equation you can use, and then find out the Y2, because in these two equations now only unknown is Yi, that is Y1, Y2. If one is known, another one can be known. So, Y1 you can write it as x1 alpha gamma 1 alpha P1 sat by P, or x1 beta gamma 1 beta P1 sat by P also you can do. When you do, you will get 0.999. So, at this pressure the vapor is almost pure in component 1, only small amount of negligible amount of component 2 is there in the vapor phase. So, Y2 alpha you can get x2 alpha gamma 2 alpha P2 sat by P, or x2 beta gamma 2 beta P2 sat by P you can do, then you can get Y2 as 0.001, or you can simply do 1 minus Y1, then you will get Y2 as 0.001. So, now equilibrium composition of VLLE also we obtained. We obtained the equilibrium composition of VLLE part as well. So, now what we have to do? We have to draw phase diagram. So, from Van Laar model at 37.8 degree centigrade and 4.69 bar, the isobutane, that is component 1, and then perfurol mixture, that is component 2, has two liquid phases and a vapor phase all coexisting at equilibrium. Though the vapor phase is having almost pure isobutane. So, now we will be drawing phase diagram of this system. The pressure that we got 4.69 bar. So, there this one, that line. So, from the calculation we know that for isobutane, so as x1 we are plotting x1 and then y1 we are plotting, okay, P versus x1 y1, that is what we are calculating, because temperature is fixed, pressure we can find out for different x1 y1 x2 y2 for different phases, alpha and beta liquid phases, and then vapor phase also we can know the calculation from these equations, and then you can draw this figure. Okay. The isobutane mole fraction we have seen that it is changing in the range of 0.1128 to 0.9284. Okay. And above the bubble point pressure of 4.69 bar, only two liquid phases will exist. So, first that is what we try to locate. We try to have the line, this line up to this part, what we have, V line of P is equals to 4.69 bar system pressure, and then we locate a mole fraction 0.1128 and then 0.9284, and then above this pressure we know only liquid phases would be there, and then two liquids are coexisting. So, above this pressure LLE region would be there. So, draw a line from here like this at mole fraction 0.1128 and then 0.9284 here, and then along this tie line pressure, constant pressure. So, this region will be having only LLE region. Below this region we will be having VLE region, and then this line is nothing but VLLE line, and this line is nothing but VLLE line. And then we know this L2 region small in this isobutane fraction, right, is rich in the other component. So, this other component is whatever furfural. So, this region is there, whatever this is there, X liquid 2 region, that is furfural rich region. So, whatever the region above this pressure of 4.69 bar is there, that is LLE region and indicated as LLE region in the phase diagram. This is how we can construct these phase diagrams. And then the region indicated as L2 only, whatever this region is there, right. So, that region only one liquid phase is existing, that is rich in furfural, that is the second component, and dilute in isobutane, rich in furfural and dilute in isobutane. So, that region we are calling L2 region. So, that line from here 0.1122 is 0, you can draw a line. It is not exactly 0, whatever 0.012 composition that is there, that we have found in the calculation, that line. So, it is almost close to 0. So, this line you can combine like here, like this. So, this entire region now you have liquid 2 region, or beta liquid phase, or second liquid phase, which is rich in furfural. Okay. And then whatever the region L1 is there, that is rich in isobutane. So, you can see this region, the entire region is this region L1 is rich in isobutane. So, this is what we can have. Okay. So, this L1 region is rich in isobutane because larger X side, X1 side, because you are plotting isobutane. So, larger that side, pure liquid is there. And then there is a vapor phase also, that vapor phase is there only Y1 0.999, almost touching this right scale here. So, only this small region there is a vapor, only in this small region close to this corner, right corner here, you have a vapor phase. So, now you can have this P X Y diagram at constant temperature. So, in the region denoted VLE, a liquid phase dilute in isobutane is in equilibrium with a vapor phase that is rich in that component. So, that is the VLE region. So, now we indicated LLE region, we indicated the furfural rich liquid region, we indicated the isobutane rich liquid region, and then we indicated the VLE region also, which is where vapor is in equilibrium with a liquid phase which is dilute in isobutane. That is what we can see here. Okay, that also we indicated. So, indeed at pressure above 1 bar, the vapor phase mole fraction is mole fraction of isobutane is greater than 0.111 and appears coinciding with the right axis on the scale shown here. Okay. So, neither the vapor liquid tie line nor the liquid liquid tie lines are shown, because we are interested in drawing the phase diagram. So, that at any given constant pressure, a horizontal line if you draw, so that tie lines accordingly their different phase composition etc., you can find it out here. So, now here you can compare. So, there is a region of very low pressure and high isobutane mole fraction in which only vapor exists as indicated by V here in the corner, this V, because Y1 we know it is 0.999. So, that is the reason it is there in this part. This vapor phase region starts at the pure furfural side of diagram at pressure below 0.005 bar, that is the vapor pressure of furfural, and continues to up to almost 5 bars, that is 4.956 bar, that is the vapor pressure of isobutane for pure isobutane. So, this region, this line you can see a very almost touching this wall, and then this line goes up to almost 5 bars like this. So, that is the vapor region, right. So, now here what we can see, if you compare this PXY diagram with TXY diagram of methanol N-hexane system, we can see there in TXY diagram we have already seen in the previous lecture, there was a kind of azeotrope, minimum boiling azeotropic mixture, this one at the given conditions. But here in this PXY diagram there is no azeotrope at all, because the vapor pressures of this isobutane and then perfurol are very much different from each other. So, though there is a non-ideality in this isobutane and perfurol system, the vapor pressure of these components are far away from each other. So, that is the reason there is no azeotrope here, but still we have a kind of VLLE. So, the region which is separating LLE and then VLE region here, the straight line is whatever is there, that is the VLLE line. Okay. So, it is not necessary that we should always have a kind of azeotrope in order to have a kind of VLLE, it is not required. That is, it is not necessary to have azeotrope in VLE in order to have that VLE coinciding with the LLE before the temperature of the system reaching the upper constellate temperature. That is not required. That is as a one simple case we have taken in the previous lecture and discussed. Okay. So, as already mentioned in the previous lecture, different types of complicated phase diagrams may also possible. Okay. So, now what we do quickly before winding up this lecture, we have a comparison of these two whatever the phase diagrams that we have seen in a couple of minutes, and then wind up the lecture. Comparison of phase diagram. So, TXY diagram that we have drawn for methanol N-hexane system in previous lecture is given here. That is, TXY of methanol and N-hexane at fixed pressure of 0.133 bar is given, shown here, and then bottom figure indicates the PXY diagram of whatever the isobutane and then perfurol that we have just take an example problem. We solve that problem and then draw this phase diagram. So, we are comparing these two. Okay. Bottom one is PXY of isobutane and perfurol system at fixed temperature of 37.8 degrees centigrades. In the TXY diagram here, vapor region is at the top of the figure, obviously, because this is TXY, and then whereas the vapor region here, vapor region in the TXY diagram here at the top, whereas in the PXY diagram vapor region is at the bottom, at the lower pressure side. Then system in the TXY diagram, system is very non-ideal and display azeotrope, because vapor pressures of methanol and N-hexane are almost close to each other. They are very much similar to each other, close to each other. So, that is the reason there is a azeotrope here, right. But in the case of isobutane and then perfurol system, though the system is non-ideal, there is no azeotrope here. There is no azeotrope here, because the vapor pressures of these two components differ from each other by order of 3 orders of magnitude, right. So, because of these very different vapor pressures, even though there is a non-ideality in the system of isobutane and perfurol, there is no azeotrope formation here. Azeotrope formation may take place in general if this vapor pressure of the components are very close to each other. Okay. And then VLE, that exhibiting azeotrope intersecting the liquid-liquid phase boundary here in this case of TXY diagram, and then we are having a kind of a VLLE line in the case of TXY diagram. And then vapor composition in VLE region is indicated by common intersection of two dew point curves with LLE line, as already discussed. Such system is known as heterogeneous azeotropy. Now further what we can do, if you compare the, or if you do upside down of one of this figure, then we can see the other one. So let us say if the top figure Txy, if you put it upside down, you can see as a kind of a bottom figure you can get, but without azeotrope, in the bottom one. That is the only difference. So top figure look more like a bottom one if it is turned upside down, and then there is no azeotrope kind of thing. Okay. So finally this is how we can solve the problems associated with the vapor liquid equilibrium, and then construct phase diagram, and then depending on the temperature and composition, or depending on the pressure and composition, when one can indicate the different regions, single liquid regions, two liquid regions, vapor liquid regions, etc. all those things one can do. And remember, all these calculation we have done for the cases where the pressure is in low to moderate range, so that we can segregate the governing V LLE equations in two parts. LLE is independent of the pressure part, and then solve the LLE composition independent of the pressure, and then using that LLE composition you can find out the vapor composition, so that you can find out the composition of all three phases, that is one vapor phase and then two liquid phases which are coexisting and then at equilibrium. So, the references for this lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prousnit et al., then Chemical, Biochemical and Engineering Thermodynamics by Sandler, and then Introduction to Chemical Engineering Thermodynamics by Smith et al. This entire lecture is prepared from this reference book. From this reference book we have prepared this entire lecture, that is Sandler, Chemical, Biochemical and Engineering Thermodynamics by Sandler, including the example problem discussed also can be seen in this particular reference book. Thank you.